diagnostics which I've developed for cross-validating new different observation types. One moment. Yeah, from what I can see, there are mainly two reasons why we are interested in observation impact. One is that we have to make decisions which observations we want to simulate, and the other is that we have to put a lot of work for the observations which we do assimilate, which often means that we need to identify problems. And for this, I have developed a cross-validation tool which allows us to compare observations under some conditions directly with other observations. So it's about checking the consistency of the consistent use of two observations, or more precisely of the ops minus first guess departures of these observations. And I do this by comparing them directly with the background error covariances, in principle the P matrix projected into observation space by the observation operators. But in our system, I'm working with the ensemble Kalman filter. This is corresponds to the ensemble covariances, or more precisely, the ensemble covariances multiplied by a localization function. So how do we relate these ensemble covariances to observations? It's a very well-known relation here. I think that the covariance of the ops minus first guess departures can be written just as a sum of background error plus observation error. And if you have two observations here, a known diagonal element of two observations which are where the observation error is uncorrelated, you end up with an estimator for the background error covariance from the observations, which we can compare with what we get from our ensemble. And there's a straightforward test for this relation. So this is a basic relation where I would say the deeper reason where the skill of my diagnostic comes from, and we can test it in some way quite straightforwardly. Here for temperature measurements from radiosondes and aircraft. So if we put the left side on the x-axis and the right, we get from all the products of ops minus first guess departures, we get a green cloud of green spots here. And when we do some averaging, and we can average further to reduce some noise, we get the colored lines out of this. And if the equation up here was completely true and the averaging was completely sufficient, then these colored lines should be on the black diagonal. So I thought this doesn't look too bad. You can do it also for other type of diagnostics, other type of observations, like here relative humidity. And I did it for many cases, and in general, I found it looks surprisingly good, I found. But what does it mean for data assimilation? And there comes my cross-validation diagnostic, which is related directly to an impact function and which is more flexible, that you can collect data in different kind of bins. So this cross-validation diagnostic has been derived originally from the full FSOI verification function, which is usually split into different components related to different observations or observation types. And what I've done, I've partitioned these components further into two components. And the blue one is my cross-validation diagnostic, and the red one, the other component. Unfortunately, I don't have time in this talk to discuss it, but there is a paper which I will advertise at the end of this talk. So the cross-validation diagnostic, because of the minus sign, it has to be larger than 0. This is actually a necessary condition to get a beneficial impact from an observation type at all. And to tell you a little what it shows you, this component of the FSOI score, I use, as I said, observations for verification. And when I assimilate other observations, the background can be put either closer to the verification data or further away. And what the original FSOI method asks is whether the assimilation improves the fit to the verification data. When I do cross-validation, I ask a strongly related but simpler question. It's whether the model is drawn into the right direction. Simplicity here, I believe, is a great asset, because in the end, I want to interpret results I'm getting with my diagnostic. And mathematically, pulling into the right direction turns out to be that the product of an ensemble covariance multiplied by the 2 ops minus first guess departures has to be larger than 0. And from this, I constructed this. You can construct this diagnostic by summing over, by a weighted sum over a large number of observations. And in the diagnostic tool, or in the results I will show here, this diagnostic is always represented by the black curve, by the blue curve. But we can do better than just asking whether it's the blue curve is larger than 0. There is the green curve, which is a reference curve, which is obtained by exactly the same sum, but the product of the ops minus first guess departures are replaced by the background error covariance, which means nothing different than by comparing the green and the blue curve, we are making a test, an indirect test of our central equation I mentioned at the beginning. So for me, cross-validation means comparing in these graphs the blue and the green curves, but of course there are other curves produced by this diagnostic tool, and an important one is the science squares, which is a noise indicator. And if the blue curve gets anywhere close to this sine curve, you have to worry strongly about statistical significance. I will also show you some scaled graphs, and scaling here means basically just that in each bin, all the curves here in the upper graph are divided by the same number, which is bin dependent and which is chosen in a way that the green curve is always between 0 and 1. For details, again, you have to read the paper, but this allows us to compare the green and the blue curve more conveniently. There's also a red curve here, which is related to the second component, which I also don't talk about much further here. An important variant of my diagnostic are single observation experiments. And if you're mainly interested to see whether two observation types are processed consistently, single observation experiments are actually a very good choice, I would say. One, you assimilate one of them and the other you use for verification. And it has the advantage that the ingredients which we need for our diagnostics are more easily computed, and you can apply it also for observations, even for observations which you have never assimilated in your system. So that's the diagnostics, and the strategy now was to collect statistics in a large number, very different bins, which might tell you different things about the quality of your observations, and to do it for a large number of observations, starting with well-established in situ observations, which you can take as a benchmark, and as a test for, also a test for the ensemble covariances. And then in the second step, of course, to use this for cross-validating less trusted observations. A good example for this was the testing of atmospheric motion vectors. Here on the left side, you have verification of wind data from aircraft with radiosonde data. And on the bins here correspond to the vertical distance between the two measurements in logarithmic pressure space. And on the right side here, the results for atmospheric motion vectors. They show you that the blue curve is always larger than 0. That means they are clearly beneficial. But we also see they are clearly less beneficial, less optimal than in situ measurements. This peak at no vertical distance, which is very typical for all in situ measurements, is completely missing in these data here. That shows you that there are some suboptimalities, and it is consistent with reported height assignment problems. So if anybody has an idea how to improve the height assignment, or another idea how to improve the processing of these data, I believe this tool can be very useful for testing and tuning your ideas. Another example I would like to show you came when I compared EMSU channels with aircraft and radio sounds, where I had here for channel 7, for example, I had an extremely good correspondence with radio sound temperature, but quite poor with aircraft temperature. So where does this difference come from? To look at it in more detail, I looked where the contributions to the blue curve in the verification against aircraft measurements come from geographically, and I found there's a region over the North Atlantic which has a huge impact and where you have a lot of negative contributions. Brown in colors here are negative contributions. But for the same region, verification against radio zones gave completely positive impact. So this motivated to test aircraft against radio zone temperatures just for this red box area. And yeah, we see it's not very good, and it actually became substantially better when I removed the residual. If you remove the residual biases in these bins, you still have residual biases, and with this diagnostic, you can easily check if you remove it, what would be your score then, and that's what you have from the cyan curve, which is a clear improvement. I also found that there are two types of aircraft data in this red box region, and one of them, the under data, actually showed excellent impact, and the problem is were really the Arab data. If you look where the Arab data are, the most of the impact is actually over the North Atlantic. So it's not surprising when we removed them from our operational system, we got a clear improvements of forecast skill over Europe. So green colors was a verification against analysis, and green colors are positive improvements in verification. So if I have the time, I would like to show you some other results from a different application, which is about verifying covariances. If you have two trusted observations, you can also verify the ensemble covariances with this. This is work which I did with Christoph Schraff in collaboration. Christoph was a little concerned about how physics perturbations, which had been introduced in the ensemble, what they do with the ensemble covariances. These physics perturbations had been introduced to increase the ensemble spread. And the data I'm showing you here are covariances between surface pressure and upper air temperature. There is no vertical localization applied for computing these curves here, and the curves show you where the curves show you where the covariances would be if no application, if no vertical localization is applied. So the green curve, to remind you, shows you where the ensemble has covariances, and the blue curve shows you whether the observations agree with this. So in the perturbed run, I'm showing you here the latent heat nudging coefficients had been perturbed, which from the green curve you see this led to a huge increase of the ensemble covariances, which actually rise quite dramatically towards the tropopause. And at lower levels, the observations seem to follow quite nicely, but at higher levels, at upper levels, you have only noise, but also in the control, you have only noise at upper levels, which means nothing, but you have to, assimilating such data obviously requires localization. Interestingly, there's a region where the control has almost no impact, no skill, but the perturbed run does. And found this quite intriguing. So I produced the straightforward tests of the covariances I showed you at the beginning, restricted to this region here between 600 and 750 hectopascal. And you see that in the perturbed run, there are many data points with quite large negative covariances, which don't exist. You have no such data in the control at all. And the good news is these large covariances offered by the ensemble here, the observations agree with this. So this showed that Christoph had been concerned whether the perturbations could do harm to the covariances. For most cases, which I had not shown, they didn't do much, but here they even showed, I think, would say quite clear improvement.
2-minute warning.
Yeah, okay, that's good. I already come to my last slide. I hope I gave you some impression about the kinds of insights one can get from the covariance-based cross-validation methods, which I'm working on. That you get you get a diagnostic for what the data assimilation system has as covariances, where it has covariances, and then whether the observations by the blue curve, whether they agree with it. You can use it for cross-validating different observation types, or for I've shown you an example also for cross-validating the employed covariances in your system. If I have to pick two things, I think they are particularly suited for assessing residual biases in your data, and also to to assess localization height or the localization region for known local observations, to assess regions where the ensemble covariances are reliable. And as I had mentioned before, there has been a paper published this summer in the Quarterly Journal where large part of this talk and also all the mathematics behind these diagnostics has been written down. Yeah, thank you very much. And thank you for listening.
Thank you very much, Olaf, for this very interesting talk. And I would encourage everyone to write more questions in the OPAD. I already posted 3 questions in case people need more time. And I think we'll start with the first question, which is, so your approach relies on ensemble-based estimates of background error covariances. How does the ensemble size and sampling errors affect your approach?
Yes, I mean, ensemble size and sampling area obviously assesses the quality of the covariances, and my approach. I mean, if you want to cross-validate observations, I rely on the quality of these covariances. If you say you just want to want to diagnose how well your observations are processed by your system, then you're processing kind of the two together, the quality of your covariances and of the observations. And then I would say the diagnostic is good for showing you this combined impact. Yeah.
So as there is another question, I will ask another one. So I was wondering, so your approach allows you to compare different observation types and also to find detrimental observations. Would it be possible or make sense to remove blacklist strong detrimental observations and then recompute an analysis to get an improved forecast? Would this make sense?
Yeah, I mean like this proactive quality control.
Exactly, yeah, like observation targeting, proactive quality control. So did you think about that?
Yeah, I mean, I you know, from the statistics I've shown you at the beginning, you remember the green cloud of spots if I don't do no averaging at all. I had the impression that with my diagnostic, I had a huge noise if I just look at individual cases. So it strongly depends on averaging, and for averaging, I need a bin variable, a variable which tells me what I want to, which group of observations I want to average. So I could, if I had groups of observations where I have doubts and I check it, and then it could make sense to, to remove observations in a given bin. But
okay,
for
okay, so you
individual
could not.
observations, I would be quite cautious.
Okay, so you cannot blacklist individual observations, just groups within a bin that you determined as detrimental.
I think so, because the noise shows that even good observations, because of random errors, have negative impact of intervention. So
great, thanks. So perhaps one last question. So if I understood it correctly, you use observations for verification. So how do observation biases affect the cross-validation?
yeah, observation bias reduce the quality of your data.
Okay.
And as I've seen, if the quality is bad, you get bad impact. And then and when you do with my diagnostic, for the bins you have chosen, within these bins you can remove the bias artificially and see what the impact of it is. You can also first of all you can check whether there is such a bias and whether it has impact. So that's, I think, a nice feature of this diagnostic.
Okay, so then one last question by Risto. So what is the main advantage of the covariance-based diagnostics to more traditional methods like de Rosier?
Yeah, it's, I mean, de Rosier gives you the error I mean, we're using de Rosier to compute observation errors. And this is here to diagnose impact of the observation here. I mean, to see whether you have a positive or negative impact. I mean, with de Rosier, maybe if you get a very large error which you would need to assign, then it shows your observation. You shouldn't give it any impact, any weight. So the impact is bad. Maybe you can derive that, but you would. I have not looked at de Rosier in this way systematically and don't know how far you get. And also for de Rosier, I'm not completely sure about a systematic derivation where the limits, in which situations you have limits and should be cautious. Whereas here, I have some error measures, some noise indicators and stuff. I think my diagnostic is much more easy accessible. You can see better what you are actually doing, I think.
Okay, great. Thanks, Olaf. So you can stop sharing, and I will give one short announcement before we close today. And before sharing my screen, I want to thank all the speakers and also my co-conveners and organizers, so Niki Privé, Daisuke Hotta, and Risto Chilpiski for helping to organize this session. I also want to thank all the speakers for the great contribution. I think it was a very interesting session. And on December 2nd, we will be back with a session on land surface data assimilation in the Europe-America time slot. And so if you have any contributions for the non-Gaussian data assimilation session and ocean data assimilation session, please submit your abstracts on our homepage before December 4th. And so for people who tuned in later, today we announced a special event which will be on operational data assimilation systems, particularly the system of JMA and ECMWF, which will take place in March. So thank you all, and have a great weekend. Bye-bye. So Lars, should we go to the test session?
Yeah, let me see if I practice session.